Hey everybody, Paul Abernathy here. Welcome to another episode of Electrical Code Academy, where we talk about the National Electrical Code. Our Fast Tracks program has been widely successful. We have electricians all over the country in our program, whether it's preparing for an electrical exam or just to become more knowledgeable in the National Electrical Code. We have a program for every application. So again, we thank everybody for supporting us. Also, you'll see there's a new URL right here below me. That's the Fast Tracks tube. That is going to be the platform where we have all of our videos in the future. So make sure you mark that down because that's where you're going to go to see a lot of our videos in the future. So check that out. Okay, let's look at it. So what we're going to do today is we're going to look at the standard method when it comes to calculating a load for dwelling. And this is also going to apply to individual dwelling units of a multifamily dwelling if you're doing an individual dwelling unit. But again, one family dwelling is what we're going to kind of focus on today. So we're going to look at the different steps because I get a lot of questions from people about the different steps. And of course, in our Fast Tracks program, we go over this very deep and detailed. And we have some little forms that you use to work through, and it really makes it easy to understand all the elements. So we are going to use our Fast Tracks in this lesson so you can kind of get a little bit of a peek of what you're going to get and how deep it gets. And of course, we have Wednesday night sessions for you to come. If you're a member of our program, you can come and ask me questions on Wednesday nights. Again, it's a great place to meet every Wednesday night. So if you want more information on our Fast Tracks program, we'll give a link down in the description. But we're going to give you a little sneak peek. Here we're going to be looking at Unit 8, which is one of the more difficult units in the program. That when I'm doing a competency review, people struggle with it because all the information is here, but kind of putting it in order so that you can understand it. Now, we recommend that you download our form, which walks you through each step. Now, it's not available to you if you're not a Fast Track student, so don't email me and ask. You have to be a member of the program to get our form, and it walks you through the steps. And if you do it enough, you will become very proficient. And any dwelling you look at, you'll be able to do a calculation. Okay. Now, we're going to do the standard method. You need to know how to do the standard method for exams. In the real world, you're probably going to use an optional method, which is under Part 4 of Article 220. We're going to be using the standard method, which is under Part 3. Another reason you need to understand the standard method is when you're sizing the neutral, you can only use Part 3. You can't use the optional method for sizing a neutral. Okay, why? Because 220.61 that deals with neutrals is under Part 3. It's not under Part 4 because sheerly the way it lays in the code, then you can't do it. Okay. All right, so let's get into it and look at a little bit of it, and I'll walk you through it. And don't worry, we're going to make it easy to understand straightforward topics. Okay, so the first thing that I need to do, any calculation, whether it's optional or even a standard method, I have to compile the information. I need to know what the square footage is in order to do this calculation. I need to have all that information, right? So in the Fast Tracks program, we kind of walk you through each element so it makes it easier to understand, because at the end of the day, you want to be able to walk away from all this and understand the calculation. And so that's how we kind of break it down. So if you look at your screen here, it says Unit 8-1 is talking about compiling information essential to a load calculation. What are the stuff that you need to gather in order to be able to do a single family dwelling calculation using the standard method? But in this case, you need this information as well, even if you were doing the optional method. So let's kind of go through it. So 8-1A says total floor area square footage. So A, as you can see here in the illustration, and I'll kind of walk us through here. A is talking, in this case, here you see the front porch, okay? It comes in, right? Here's your rails, all this type of stuff, okay? So coming in, the front porch square footage, it says, A, open areas of porches are not included in the calculated area, a floor area of a dwelling unit, and it states that in 220.11. Of course, we'll go look at 220.11 and see what the code says. So what that means is when I'm looking at a blueprint, I'm looking at the floor area, that if there is an open porch on the front, then you do not count that area as being part of the floor area. So in this case, here's the front door. You're coming in the front door. Here's the front porch. All of this area in the front porch, you don't count that. That's the open porch. That's not a part of your square footage that you're going to need for our calculation. So that's kind of getting that out of the way. B, it says scale rulers are also used to determine the location of outlets, receptacle, lighting switches, and all that type of stuff. So again, getting familiar, if you're preparing for an exam, getting familiar and understanding how to read a ruler in order to be able to take these measurements and all that type of stuff is essential. The next thing we look at is C. Says before a scale ruler can be used to determine dimensions, the scale must be produced on the blueprint and it must be known. So if you actually have a blueprint, it'll tell you that it's 1/4 of an inch per foot, 1/60 of an inch per foot. It'll state that on your blueprint. So it's essential for us to be able to know how to determine the floor area of a blueprint so that we can apply these rules. Okay. Now, you could have just a residential drawing that is a pretty simple drawing that gives you feet, the length and the width and things like that. But you need to have this information in order to be able to determine what our square footage is. Now D here is just giving you some references here to the rule. It says scale rulers are useful for determining the square footage of a structure, house, blueprint, or whatever that typically do appear on your blueprints. It'll give you a scale like 1/4 of an inch equals a foot, that type of thing. And you might need to do that in order to find out what the dimensions are. All right. And of course, E says a regular tape measure, ruler, yardstick, whatever can be used, but the use of the scale ruler makes the job much easier. So in this case, a blueprint could say a 1/2 inch per foot. And so if I'm looking at a blueprint, I need to know that if it is a 1/2 inch per foot and I measure it out, then I can see that if it is a certain number of 1/2 inches, then I can translate that into how many feet we're doing with a room, and that'd be the length and the width. Okay, so that's just the basics. You probably already get that. You probably know how to use a slide rule, or not slide rule, but a regular ruler, that type of thing. So that's just kind of setting the foundation. Now, when we go look at the code real quick, what we're looking at is it made a reference to 220.11. And in 220.11, let's read what it says here. It says the floor area of each floor, okay, shall be calculated from the outside dimensions of the building, dwelling unit, or other area involved. For dwelling units, and that's what we're talking about today, it says the calculated floor area shall not include open porches, like we said. It shall not include garages. That changes for the 2023 NEC, but right now you're in the 2020, does not apply to garages or unused or unfinished spaces not adaptable for future use. An example of that would be like an attic. If an attic has pull-down stairs or simply a scuttle hole, or it's not designed to support weight, then it is not adaptable for future use. If it has permanent stairs getting to it, the flooring is designed to be load supporting, and it could be adaptable for future use, then you're going to count that in your square footage. If I have a basement, for example, even if it's unfinished, if it is adaptable for future use, and it would be, you could finish it off, then you have to take that floor's dimensions and add that in your square footage. So if I have a basement, a first floor, and an attic, the basement, if it was unfinished, you still got to count the square footage based on the outside diameter. The first floor, you do the same thing based on the outside diameter. The attic, if it is not adaptable for future use, then I would not count that. Now, if it's an attic that has stairs that are permanent going up to it, and it has the ceiling height, and it meets the requirements to be adaptable for future use, then I would have to count that square footage as well. So every floor counts, okay? So that's what it's stating in the code right here in that requirement. Okay, let's get back. All right, general information that we need to gather. So this is stuff that you need to be gathering if you're going to do a load calculation. Here's what it says. It says, gathering certain information necessary to accurately perform load calculations. What do I need to be able to do these calculations? Well, all of the essential data can be identified by simply answering the questions found on the load calculation form. And that's the form that we provide. So let me highlight that real quick. And you can do all these highlight features in our Fast Tracks program in order to call out things. And remind you, you can print any page you want in our program. Okay, so those that are interested. So in this case right here, we have a form. And in that form, it's step by step will walk you through all the gathering information. And a lot of people will use these forms even after they either pass their exam or are using this to go through our course, they will laminate these forms and keep them in their code book like a bookmark, and they'll get a dry erase pencil, and they can always work it out, and you will always know how to calculate a load on a dwelling. And we have a form for the single family, multifamily, as well as the non-dwelling unit application, like commercial. We have a form for any of those. So that's part of our program. Again, don't ask me if you can get it, because you can't get it unless you're part of our program. All right, so it says either standard or optional method. We have a form for either or, okay? And then it says enter the information on the appropriate line of the load calculation form provided with the textbook, or in this case, our course material, okay? Now here you see kind of a gathering, kind of a synopsis of the gathering. All right, so A is talking about what is the dwelling's total square footage, and shows you this is an example for square footage. Pop that out. There you go. That's what we're looking at, square feet. Area used, and you're using the outside dimensions. So 220.11 told us that. And this is a 2020 edition of the NEC. So again, we'll be doing this for the 2023 here shortly. But again, because there are some significant changes. So again, this video can't be used for the 2023 edition, only for the 2020. All right, so once you know your dimensions for each floor, you write that down. The next thing you need to do is you need to find what fasten-in-place appliances will be installed and what is their VA load for each. Okay, so here we're looking at B and B right here. You've got a dishwasher, garbage disposal right here. You got a trash compactor, attic fans. This is a water heater. All of those items are fastened in place appliances, and they're going to have a VA value. Now, they might have an amp value, and you have to do volts times amps to get a VA value. We're ultimately going to work everything down into VA. But also remember that even wattage at this stage is equivalent to VA, volt amperes. Okay. So that's that one. Then the next one is C, and C is going to be other small appliance branch circuits that are to be installed. Like in a kitchen, you have to have a minimum of 2 small appliance branch circuits, okay, at 1500 VA each, and we'll look at that. But you also will have a laundry circuit at 1500 VA that you have to account for. And if you look at all those things, you're like, okay, I have to be aware that I have all of these things that need to be added into this calculation. And I need to start compiling all this info. Here's your small appliance again. And then of course you have D, and D is indicative of a laundry circuit. And that is a 20 amp laundry circuit that's required. That is 1500 VA as well. And so you have to take that into consideration for this single family dwelling. So you have to go around and start compiling information. What else do you need to do? Well, here you see E, which is dealing with electric clothes dryers. So if you do have a clothes dryer, then you need to be aware that that is going to be a value that you have to take into consideration. And for the standard method, it's going to be at least 5,000 VA or 5,000 watts or higher, whichever is or the nameplate, whichever is greater. But in this case, it's going to be a minimum of 5,000. And so you need to understand that that's in 220.54. And you need to at least know what's going in place. Okay. And sometimes people say, well, Paul, I don't know what's being installed. I don't know the size of the dryer. Well, you know if you're putting in a dryer receptacle, then you're going to have to figure at least 5,000. But it really behooves you to stay in contact with the developer, the owner, and really ask them, what's your appliances? Can I get the appliances that you intend to buy so that I can do an accurate load calculation? Most of the time I'm going to tell you that people just use the 5,000 VA and they're going to be okay. Most of the dryers, that's going to fall within an acceptable household type of dryers range. So usually okay. But again, if you look at 220.54, it's 5,000 or the nameplate, whichever is greater. Okay, so compiling this information is not always easy, but it's part of your job. That's what you have to do. So you're going to have to ask the questions necessary to get this information. You definitely will. And then, of course, cooking equipment, whether or not there's a range, you need to get that value for the range. If there's cooktops, things like that. You need to procure all of that information because we're going to need that in 220.55 for cooking appliances. So we need to compile that information. So you got to ask somebody. You just can't guess at it. That's why we electricians get the big bucks, right? We have to ask. We have to be willing to communicate with others like the owners, the builders, or whatnot. And if it's a multifamily building and we're doing individual dwelling units, then you're probably going to have a blueprint that's going to have a legend on there that's going to give all this standardized equipment that's going to be in each one of these apartments, if you will. But when it's a one-family dwelling, you're going to have to ask somebody. You just can't assume anything, right? And then, of course, G is going to be our HVAC, our air conditioning, any heating. Maybe it's maybe there are baseboard heaters that are going in here. Maybe it's a central air conditioning with a separate heating. Maybe it's a heat pump. You need to get that information, not just because you got to run circuits to it. Obviously, you need to know the size of your branch circuit to run to everything. But at the end of the day, you got to compile and know what the load calculation is going to be. And for example, in the standard method, you're going to have to compare the heat versus AC if there are non-coincident loads. Means that the AC is not going to run at the same time as the heat. Then you have to look and compare the two and take the larger of the two. There's the only way you can do that is to know these values. So ask for these values. Again, it's nothing wrong with asking. You're not assumed to know any of this when you're bidding out a project. You got to ask somebody, okay? Now, interesting, when you do the optional method, you still need to know because you're going to take the nameplate value when you're doing the load calculation. But in the standard method, I really need to know because I'm comparing non-coincident loads. Now, with a heat pump, you don't necessarily have a non-coincident load, so you're just going to take the nameplate values of it and work with it. But if you did have central air and separate heating, they wouldn't be non-coincident loads because they either or could be on at the same time. Then you need to know that so you can do your calculation properly, okay? All that stuff should make sense, but if it doesn't, look, our Fast Tracks program is designed to teach you these things, and if there is any questions, you can come to our Wednesday night session and ask us. Oh, so this is the form that you've heard me talk about. So this form, you can print it out. We also put it in a folder in your Fast Tracks program so you can get a higher definition copy that you can print out. And as you can see, it goes by 1, 2, 3, 4, 5. It gives you the code references. The reason we do this in this form is to slowly teach you the different steps so that when you get into the real world, not just on an exam, but in the real world, you understand that as long as you know how to do each step, that no matter what question that is put in front of you, you're going to be able to answer the question. So that's what this form is designed to do. Now, this isn't designed for you to take to an exam. And I've had people ask that before. It says, why should I learn to use this form if I can't use it in an exam? This form was never designed to be used in an exam. This was designed for you to use it step by step to learn the code sections that are applicable to each one of these steps so that you can be able to regurgitate it. If somebody asks you a question on any one of these steps, you will know how to do it. For example, a lot of electrical exams, they're not going to ask you to do an entire calculation, but they could ask you any one of these little steps. And if you learn these steps, no matter what they ask you, you'll be able to answer the question. And that's why we use this. And this is just part of the learning exercise. Now, we have one for the standard method. We have one for the optional method. Okay. Same when you're doing the multifamily, same concept. Okay. So anyway, you print this thing out and you get it laminated or print out as many of these as you want. And you use a new one every time you do a calculation. Okay. And if you want to get really creative and you really want to get good at it, then you can make up your own fictitious dwelling with a bunch of different appliances and different things, and then use this form and test your skills. See how well you're doing. And if you go step by step, you shouldn't have any problem. Okay, so that's the form. You can print off it in as many as you want. Okay, so in our sample dwelling, we're going to work with the sample dwelling. And here it's very indicative of what you see in a normal dwelling. And we're going to remind you that in our example, assume a water heater, clothes dryers, counter-mounted cooking units, that's like a cooktop, wall-mounted ovens, and electric ranges, for example, or even the electric heat. All of that could be conveyed in kW. but it's going to be considered equivalent to kVA. And all of that's covered in the National Electrical Code. It lets you know that it's considered equivalent. It states that many times. When you're talking about ranges, it states that. When you're talking about dryers, it states that in 220.54, 220.55 for ranges. Over and over again, it reminds you that as far as Article 220 is concerned, watts are equivalent to VA. kW is equivalent to kVA. Ultimately, at the end of the day, I want to work everything out into VA so that I can end up dividing that by the voltage for the building, and that's what's going to give me my amps. But just know that they're synonymous as far as this stage so that there's no confusion regardless of either term that you use. So here's our dwelling that we're going to be working with. It already gives you the outside dimensions. Tells you that it is 35 by 55 feet. So you can just do 35 times 55. That's going to be your outside dimensions. It also tells you that it's a front porch, okay? And it says that this is included within the outside dimensions. So this 35 by 55 includes the porch. So obviously we have to do 7 times 10, that's 70 square feet. And we have to subtract that away from the value for that 35 by 55 foot outside dimension, right? Because it's telling us that it's included in there. So we want to take that out. Why? Because 220.11 said what? Don't include open porches, okay? So there you go. So in our example here, we've got small appliance, and we've got, let's see here, we've got 4 of them. So there's 4 small appliance circuits. So the National Electrical Code tells us that 210.11, that it's going to tell us that we have to have at least 2 small appliance branch circuits. And of course, they're going to be 1500 VA each, right? Well, in our case, we have 4. For every small appliance branch circuit, it's going to be 1500 VA. 2 is the minimum. You have to have at least 2. If I have 4, guess what? We still have to account for that at 1500 VA for each one of those. Okay? If we had 6 small appliance branch circuits, that would be 1500 VA each. You with me? So next we have the laundry branch circuit. And just like the small appliance branch circuit in 210.11, it tells me that I have to have at least 1 laundry circuit for this dwelling unit. Okay? And that would be 1500 VA. Now, in our case, we know that they're installing 2 of them. Okay? So we're having 2. So what does that mean? That would be 1500 VA volt amperes for each one of those. Okay? Now, again, so that we don't get lost on that, I want to make sure that everybody is totally familiar with where all that comes from. So let's go on and jump down to 220.52 really quickly so you can see where the VA value comes from. So here you see small appliance. Let me go over to the computer, to the code real quick. So here we're looking at small appliance circuit, and we got 4 of them in ours. But here's where it says in each dwelling unit, the load shall be calculated at 1500 VA for each. So we have 4, so it's 1500 times 4. Okay. Now, when it came to that laundry, here's where we saw that at right here. Same thing. It's not less than 1500 VA shall be included for each, okay, 2-wire laundry branch circuit. Okay. And so we have 2 of them here, so that's 1500 VA for each one, right? So again, remember, there are minimums, and then it's whatever you're dealing with in your actual install. In our case, we have 4 small appliances, we have 2 laundries. All of those are going to be 1500 VA each, okay? So the next thing that we've got here is we've got some fastened in place appliances. We have a water heater, and that is 4.5 kW. So that's 4,500 watts. K being kilo, which represents 1,000. So 4.5 times 1,000 is 4,500. Or you could get familiar with just seeing 4.5 K, then you know that that is 4,500 watts. Okay. The next is the dishwasher. And in this case, the dishwasher tells us that it's 10 amperes. at 120 volts. Now, here's something I like to do right up front when I'm looking at this. So if you were doing a calculation for a dwelling and you have all the information here, what you want to do up front is go on and get the VA values that you need. And so I'm going to do that here, just like you would do that, so that we know what we're working on later to make it simple for us. So since we're working things out in VA, here I've got the first thing, and that's 10 amps at 120 volts. All right. Now, we don't have to do the water heater because we know that 4.5 kW is synonymous with 4.5 kVA or 4,500 VA. So there's nothing that we have to work out for that. That one's easy. But when we got to that dishwasher, it gave us in amps and it gave us volts. We have to get this to a VA value. So you simply remember that your Ohm's law is to simply take the amps times the volts. So I'm going to do the math, trusty calculator, and I'm going to go 10. I'm going to do that times 120. And again, use the voltage value they give you. You're going to see a little later that we're going to use 115 volts. Use what's given to you here, okay? All right. So in this case, that would be, let's see here, volts times amps would be 1200 VA. So I'm going to write that down. So this dishwasher equals 1200 VA or 1.2 kVA if you wish. And so that's the value there. So remember that because you're going to need that later. The next thing we're looking here is this in-sink waste disposer. Now, in this case, it gives us in horsepower, so that signifies we're dealing with a motor, right? So we've got half horsepower, but we still need to get this to a VA value, right? So what do you do with motors? Well, we have to go to Article 430, and we're trying to look for the full load current, because once we find the current, which is ampere, then we can multiply that by the voltage, and that's how we can come up with a VA to use in our calculation. So where do we go for that in the code? Well, when we're dealing with single phase, we want to go to 430, 248, okay? So let's go look and see if that's where we need to be. So let's see, I'm going to go to code. And again, we might, let's see here, 430. And we're going to go to the FLCs. And let's go 430. And let's see, go to the tables real quick. All right, so here's the tables. Here's, let's see, 247. Maybe that's the one I need. No, that's DC. I said 248, right? Okay, let's go down to 248. There we go. So this is the single phase that we're working with, all right? So I want to go down, and remember, we're talking about 115 volts because it's said in the question. So that's this column right here, all right? So we're going to go down, and this is, I believe this is 1/6 horsepower. This one is 1/4 horsepower. This one is 1/3 horsepower. This one is 1/2, and that's what we're looking for, 1/2. So we're over here. Here's the 115. Here's the 1/2. They converge right here at 9.8 amperes. So write that down, 9.8 amperes. That is the FLC, full load current, and that's what we're going to be using here, okay? All right, so there we go. So let's go back here to our equation. And so now that we know what the FLC, C being the current being amperes, we're going to take that 9.8 and we're going to multiply that by, in this case, 115 volts. And that is going to be 1,127 VA. So we're going to write that down. So I'm going to write out disposer, in-sink waste disposer, and I'm going to write 1,127 VA. So that's the contribution from that in-sink waste disposer. All right. The next one we're looking at is the trash compactor. Now, we lucked out for this one. This is typically an appliance, even though it might have a motor in it, this is all treated as an appliance assembly. So it typically gives us an ampere rating on the nameplate. So here it's 7.5 amperes, and we again do what we did before, just like with the dishwasher. We do the amps times the volts. In this case, it uses 120. So we're going to do this one. It's 7.5 times 120. and that is 900. So the VA value for this trash compactor is 900 VA. So I'm going to write trash compactor, and I'm going to write 900 out beside it. And so that's my contribution for that fixed appliance. All right, next we're going to go on to these attic fans. All right, so now let's talk a little bit about these attic fans, and I'll highlight it. Oops, if I can highlight it. There we go. So there's 3 of these, and they're 4.8 amps each. Now, since they're all the same, okay, then we want to make sure that we just go on and add them all together in order to get us a total amperage, and then we can multiply that by the voltage. Now, they've already done that here. That's where that 12.6 comes from. Basically, it's 4.2 times 3 because there's 3 of them. But remember, on an exam or in real life, you may have to add them up like that and then come up with the value. And as long as they're all 120, then you can simply take their amperage and you multiply it by 120 in order to get your VA value, okay? So let's kind of do that. So I'm going to take the 12.6 times, in this case, it's 120 again. So that is 1,512. So that's my VA for these 3 attic fans, okay? So I'm going to do attic fans. So I'm just do a fan. And I'm going to put 1,512. Now, individually, I want to see what the actual VA value is for each individual fan, and I'll show you that later when we're treating them as appliances and maybe whether or not we get a little bit of a demand applied to these appliances because they are fixed in place. They're going to be mounted. So again, it's going to help you to make sure that you still have to account for the load, but I want to see whether or not they will be used as an appliance when we get that reduction possibly later. So here I'm going to take 4.2 and I'm going to multiply that by 120, and that is 504 VA per unit. So again, important to remember later. So just jot that down just so you know what the VA is per each individual fan. So that is 504. And just write that down. That's the VA. So that's individually for each one, okay? All right. The next one we'll be working with is the electric clothes dryer. Okay, we can take this highlight off real quick. All right, so electric clothes dryer. Now, interesting thing is that electric clothes dryers are not required to be installed by the National Electrical Code. No more than cooking equipment is required to be installed. However, if you do install it, you have to account for it. And in this case, our dwelling does have an electric clothes dryer. Now remember, this has nothing to do with the laundry circuit. This is a separate deal. Laundry circuit's required. We saw that previously in 210.11 for the required brand circuits. This is electric clothes dryer. It's not required to be installed in a house at all. Okay, you can always air dry your clothes. But if it is installed, you have to account for it. And so in this case, this one is 5.5 kW. Okay. Now, when it comes to the standard method, I want to talk about what's required when it comes to clothes dryers anyway. So we're going to go look at 220.54 really quickly when it comes to clothes dryers. So that I can explain a little bit of something about that. So let me get my code geared up here. And then I'll take us there so I can explain a little bit something about dryers. Okay, there we go. All right, let's go on and jump over there real quick. Okay, so here's the rule about clothes dryers. And again, it's under standard method. Okay, we're doing a standard calculation under Part 3 of Article 220. And it says the load for household electric clothes dryers in a dwelling unit or the individual dwelling units of a multifamily building would also apply here, shall be either 5,000 watts or VA, as you see in the parentheses, or the nameplate rating, whichever is larger for each dryer served. Okay, now that's where we start. Now you'll notice down here, if you have 1 through 4, it's just 100%, you get no demands. Well, we only have 1, but if you remember in our question, it was 5.5 kW. So it does exceed the 5, so we're going to use the 5.5 or 5,500 watts, which again is synonymous with VA. Okay, just kind of keeping you thinking about that type of thing. So we're not going to use 5,000 because we actually do have a dryer's rating and it does exceed 5,000, and the 5.5 kW is greater than 5,000, so that's why we're going to use it. Okay, so I just wanted to touch base with that. So that's what we're going to use here. So in our equation, you simply write, you don't have to write it down, it's right here. 5.5 kW is equal to 5.5 kVA, or 5,500 watts, okay? Or 5,500 VA for volt amperes, okay? All right, the next thing that we're going to be, and I'll take this off real quick to not avoid any confusion. You see how we're tackling these one by one, and you're going to use all this at the end to compile it, and it's going to be fairly easy to do, so bear with me. All right, so the next thing we get to tackle, and also notice how we're systematically doing this from the square footage to the small appliance branch circuits to the laundry to systematically. Now, we haven't started the actual load calc yet. All we're doing is compiling the information, okay? All right, so now let's go to this cooking. So here we have a counter-mounted cooking unit. That's like a cooktop. Okay, we'll highlight that. And we have a wall-mounted oven. Okay, so in this example, we don't have a range. We have two separate components. Now, if we were doing a branch circuit, we can combine the cooktop and the oven in order to treat it like a single range when we're doing our branch circuit calculation. But here we're kind of doing a load calc. So in this case, we have a counter-mounted cooking unit and we have a wall-mounted oven. And so we're looking for the load contribution that's involved here. So we have one's at 7 kW and one is at 6 kW. And of course, we're going to look at how we calculate that as we move through the steps when we do the load calc. So there's really nothing we have to do here right now. All we know is that there's a 7 and there's a 6. Now, before I even do that, when we get to that range load, I will go on and take you over to 220.55 to kind of give you some balance here, just like we did for the dryer. So here's 220.55 in the National Electrical Code. It's dealing with electric cooking appliances in dwelling units, in this case, a cooktop and an oven. And this tells you right here, gives you the permission to use table 220.55. Now, 220.55 is a unique table because it's actually broken into the number of appliances, but then there is a column A, there's a column B, and there's a column C. Now, you always use column C except where note 3 comes into play. Note 3 is going to come into play for us because that cooktop and that oven actually fall under column B, okay? It is between 3.5 kW and 8 3/4, so it falls right in the middle. But it also falls under column C because it is not over 12 kW. So what does that mean? So when we get to our range calculation, we're able to use column B, but we're also able to compare it to column C. And that's what it says to us in note 3. So remember, if you don't have a cooking appliance that falls under A and B, it may fall under just C. And so keep that in mind. Also remember that this column A and B are talking about a percentage, whereas column C is an actual maximum demand in actual kW. Okay, so again, we'll look at that when we're doing the calculation, but I just want to throw those subtle nuances there so you kind of know where we're going with it. But don't worry, we're going to look at each one of them for our example. I just wanted to kind of lay the lay of the land for you and show you that we're going to be using note 3 and how each column is going to work. So we already know it's 7 kW for the cooktop and the wall-mounted oven is 6 kW. Okay. The next is electric heat. And in this case, we're talking about 3 banks of 5 kW each. So it doesn't say that this is an air handler with supplemental heat. This just says, look, you have heat, 3 banks, 3 independently controlled banks at 5 kW each. Okay. That's why it says 3 banks of 5. And then, of course, you have the air handler, air conditioning, and condensing fan. That's the AC component. Now, a couple things that I'll remind you. We're going to be comparing heat versus AC, and these are going to be separate components, okay? But that air handler is going to be blowing the heat around the building as well as the air conditioning around the building. And why is that significant? Because that air handler load has to be figured in with the heat, and it has to also be figured in with the AC when you're comparing these two loads. Also, we're going to assume in this question that it is going to be a non-coincident situation where, the heat is not going to be on at the same time as the AC. Okay? Now, this would be controlled by something like a thermostat that would keep one from being turned on from the other. But let me give you some things to think about. If I have central air conditioning and I have separate baseboard heaters, then the baseboard heaters could most certainly be on at the same time as the air conditioning is on. If that's the case, then it's not considered a non-coincident load. That means you have to take into account the heating and you have to take into account the air conditioning load. Okay? If they were baseboard heating, and it said here that it's electric baseboard heating, then in that case, you would not add the air handler to that because typically with baseboard heat, it doesn't blow the heat around. It radiates around from the baseboard heaters. But the way this is written in our case, the electric heat is like central heat, and it's part of the actual air handler system, but it's separate. It's not connected to the air conditioning, central cooling. So that when you're using the air handler, when the central heat is running, it blows through the duct system. So it's going to use the air handler whether there's heating and cooling involved. Okay, and we're also going to assume that they're thermostatically controlled to the point where one can't be on when the other is on. But again, I tell you all this because, again, electricity is complicated. Calculations are one of the most complicated aspects of electrical. And so if you don't understand the nuances between baseboard heat or central heat and whether it uses air handling or whether it's a heat pump, okay, then you have to understand those different nuances. And that's the only reason I bring them up, because there's no educator out there that can give you this cookie cutter approach to it. There's so many variables. Now, when you're doing load calculations like this, you can be creative. You can do an example of a heat pump. Then you can do an example where this would be baseboard heat. You can do an example where they're not non-coincident loads. They both could be on at the same time. So again, be creative. And it's going to only make you a much better electrician the more creative you can be. Okay. All right, so in this case, we have the electric heat. There's 3 banks of 5. 5 times 3, that's 15 kW at 240 volts, so that's our heating. The air handler. The air handler is a blower motor that's going to move that heat and that cooling around the building, and that is 3.2 amperes at 115 volts. Well, we've all learned by now we need to convert this into VA while we're here. Makes our life so much easier, okay? So let's do 3.2 times, and the value in volts that they give us is 115. So that is going to be, the air handler is 368 VA. And again, calculate twice, okay? So, or do the math twice, write it down once. So I'm going to check again, 3.2 times 115, and it is 368 VA. So that's our air handler. And so we're going to write that VA down. Now, the next thing, and we don't have to do the heat because that's already in kW, just like the water heater was already in kW, okay? We can convert that to VA. That's an easy thing to do. All right, so the next thing we're looking at is the air conditioning compressor motor. Now that is 16.6 amperes. We don't need to go to the FLC. We don't need to go to the 430.248. We already are given the values we need to convert this to VA. So we're going to take 16.6 amperes times 230. So 16.6 times 230. And that is going to be for the air conditioner, the compressor motor. And that's going to be 3,818 VA. All right. So that is probably the largest motor in this dwelling, bar none, right now. So again, kind of things to think about and remember. But let me tell you something else to avoid the temptation in an exam, is that The one before that for the air handler used 115 volts. Somewhere else in here, it used 120 volts. Here for the motors, it's using 230 volts. You probably are familiar with using 120, 240 nominals. If you're preparing for an electrical exam, use what they give you on the exam, okay? In the real world, calculate it out based on the values, again, whether it's on the piece of equipment or the voltage they give you on the piece of equipment. And if you use the nominals, you're not going to go wrong in the real world. But remember, exam world is different than the real world, okay? And we're trying to solve for an electrical exam, then you want to take what's written in the question. If you're in the real world, take the value that's written on the appliance. If it lists it for use 240 volts, then use that type of thing, okay? All right, so in that case, we got that. And the last one is this condensing fan motor. And this is 2 amps, and it's 115 volts. So let's do our math again. So it's going to be 2 times 115, and that is 230 volts. So let's do condensing fan, and we're going to be writing that down at 230 VA. So only thing we haven't calculated yet is the square footage for VA per square foot for the actual dimensions, and we haven't done anything with that 1500 VAs for the small appliance and large yet. We just got the numbers that we needed to get so that when we start doing the calc, we have everything we need. So you can see I've written everything down, just like you should. And now we've got all of the things that we need to work this thing out. So let's kind of go on and get into the load calc. All right, so if you have our form, the very first line is going to be dedicated to the general lighting and receptacle load application, right? And it's going to give you the code reference that's associated with that. So we're going to kind of follow along and see how these steps work. So line 1, if you're filling it out for the dwelling that we're doing, and remember what the dimensions were of that dwelling? Do you remember? All right. If you forget, all we got to remember is that it was 35 by 55 square feet. And also remember that open porch area, we need to take that out of the equation. You remember? You can always pause the video, rewind back, come back if it gets confusing. But don't worry, we're going to look at it. And so I'm sure it'll come up again. So the first thing we're going to do right here is we're talking about general lighting and receptacle loads for dwelling units. Now, a couple things that people get lost about. They think of this thing about receptacles and 180 VA per strap, I guess I should say, 180 VA per strap when it comes to receptacles. That is not used here. We're not going to be using that for dwellings, okay? That is for commercial applications other than dwelling applications, not for dwellings, okay? We're going to be using a value of 3 VA, volt amperes, per square foot. So that's the reason we needed to know that outside dimension. All right, so let's kind of walk through. Now, if you have the form and you're a fast track student, you can follow along. A, right here, we want to go to 220.14J, and that says it requires a minimum of 3 VA per square foot for the lighting and general use receptacle outlets for a dwelling unit. So we want to go look at that real quick so we can kind of get a flavor for what that looks like in the code. So let me go on and get there, and then I'll take us over there so we can kind of look at it. And you're going to see a lot of grayed out area in the 2020 code because a lot of this 3 VA per square foot used to be in 220.12, then it ended up in 220.11, and then it ended up down here in 220.14J. So that's where it needs to be now. And it also used to be in 220.12, the table, which talked about 3 VA per square foot. Well, now that table 220.12, that's only for other than dwelling applications. So again, that's a lot of words to tell you to go to 220.14J is what I'm telling you to do. All right, so let's go there. All right, so remember, we're dealing with a dwelling unit. That's what you see right here. That's what we're dealing with. And it says for 1 family dwellings, 2 family dwellings, and multifamily dwellings, okay, the individual dwelling units, it says the minimum unit load shall not be less than 3 VA per square foot. The lighting and receptacle outlets specified in 220.14J1, J2, and J3 are included in the minimum unit load. And the minimum unit load is 3 VA per square foot. So they're already included. All right? You don't have to do anything additional for it. It says no additional load calculation shall be required for such outlets. Okay, it says the minimum lighting load shall be determined using the minimum unit load with the floor area as determined in 220.11 for dwelling units. Okay, so that is taking the outside dimensions. Okay, and once you know that, then you can do the 3 VA per square foot times those dimensions, and that's how you're going to get your VA for the dwelling here. Okay, for the lighting and general use receptacle applications. Now, 1, 2, and 3 is just to remind you, and again, I get a lot of questions here. It says general use receptacles, outlets of 20 ampere rated or less, so that's all your 15 and 20, including receptacles connected to the circuits in 210.11c3, which is bathroom, and 210.11c4, which is garage. You don't have to add any additional VA per square foot. It's already factored in. Also, unfinished basements, you still have to count that square footage at 3 VA per square foot, so that is already in the factored equation. Okay? So again, a lot of people lose sight with that. That's where you're going to get your total VA based on your square footage. Next, receptacle outlets specified in 210.52E and G, and of course, I'll show you E. E is talking about any of those outside receptacles that you might install. They're already factored in. You don't have to think and do anything else for those. They're already worked into the equation. Okay. If you have any in balconies, on porches, serving decks, already figured in. So don't have to do anything additional for that. Okay. And of course, let's see, I guess I can go down and look at G for you real quick, just so you can kind of get the context of it. 210, and we'll go down to 52G, so you can see what else is included in there. So you can actually see it in the code. There's E, and then G is the basements, garages, and accessory buildings. Again, like I said, they are already figured into this. And why does this become important? Well, say you do a service calculation and the basement's unfinished. As long as you already account for 3 VA per square foot for that basement, because it is adaptable for future use, we saw that earlier. When somebody comes along later and wants to finish out that basement, after the service has been considered, then the receptacles that you're going to put around the walls for 210.52 for spacing requirements and all that have already been factored into the 3 VA per square foot. Now, if they're doing things like adding additional specialty circuits down there, then you do have to calculate that in and determine whether or not the service is adequate to handle it. But not when we're talking about the general lighting, not when we're talking about general use receptacles. That is already figured into the 3 VA per square foot, and that's all that it was saying. Okay, you don't have to do anything extra for that. Okay. All right, so here we established that we're going to be using 220.14J, and we established that the lighting is 3 VA per square foot, and that is going to also encompass those general use receptacle applications as well. And so in our case, it's 3 VA per square foot. Now, what was our square footage? Well, remember, it was 35 times 55. So I'm going to do the math. 35 times 55, that's the 35 by 55, and that was the outside dimensions, and that's what was given in our equation. And so in that case, this is 1,925 square feet. Well, remember, it told us that that porch was part of that. So we have to take that out of the equation. And it was a 10 by 7 square foot porch. So 10 by 7 is 70 square feet. That's what you see right here. So we want to take that 1925 and just take 70 away from it. Pretty straightforward. So 1925 minus 70. And that is 1,855 square feet. So I'm going to write that down. And then as you see on your form, you fill it in right here. And you take the 3 VA times 1,855. Now, obviously, this is a one-story single-family dwelling. It is no basement. Okay, there's no attic that's adaptable for future use. It's one story. because we didn't take into account any other stories here in this dimension. So that is 1,855. Now you multiply that by 3 because it's 3 VA per square foot. So 1,855 times 3, that is 5,565 VA. Okay. Now remember, we're just starting out. That's the first part of this calculation. And there it is, right there. And that's what you should have on the form. Okay. All right. Now, we did all this math. That's how we all came up with. And again, where do you get the dimensions? All of that is in 220.11, how you do the dimensions. Now, the reason you see these little chevrons, if you're in our Fast Tracks program, when you see a chevron, what you're supposed to do is you're supposed to stop what you're doing. Grab your code book, go to that area in the code, and read it, okay? And when you go to that area in the code, it wouldn't be bad for you to highlight that area, because chances are that might give you direction when it comes to something that might see on an electrical exam. Plus, it's really good for just being a reference point when you're using your code book out in the field. Again, we know this thing gathers dust sitting up on the hood or sitting up on the dashboard or under the seat. So when you open it up, those highlights will bring you. Just don't get highlight happy. Just highlight the areas of importance. And if you go look at 210.11, you're going to see that it describes everything necessary in there. Okay? Excuse me, 220.11, I should say. So you'll look and see that in 220.11 that it's going to give you the information that talks about the square footage and all that kind of stuff, right? And how you do the measurement, what open porches are not included, things like that, okay? So we've done all that. So now remember, all 15 and 20 ampere general use receptacle outlets, except for small appliance and laundry, are considered part of that general lighting load. No additional load calculation is required. So important that people forget that all the time. Okay? We have a separate contribution for small appliance. We have a separate contribution for laundry. But these general use, due to diversity, that is all encompassing as part of that 3 VA per square foot. Okay? So on our Fast Tracks program, one of the questions that people tend to get wrong is we will give them a value and we will throw in there that somebody's coming along and finishing off a basement. And what is the additional VA contribution to that service? Well, if they did it right, that basement prior to being finished off was adaptable for future use. So that square footage should have already been figured into that 3 VA. So in reality, there is no additional contribution for the general receptacle and general lighting applications for that basement once you finish it off. So the answer is 0. So again, that only applies to your general use receptacles that you're going to run into and your general lighting you're going to run into, which is encompassed in that 3 VA per square foot. So a little subtle thing, but you need to be aware of it. All right, those small appliance branch circuits. So we've already got our number for, so we have 5,565. Make sure you write that down. That is your general lighting and general use. And also remember something, when we're doing a neutral calculation, all of those loads have a 120 volt component. So they have a neutral involved. So that is also going to be calculated when you're doing your neutral. So put an N beside that, like this. See, I always put a little N beside it to let me know that that is going to be used for our neutral load as well, because they are 120 volt loads. It's just going to save you some time. Okay, just write it down. All right, so the next thing that we're looking at is the small appliance, which also are going to be a neutral contribution. Keep that in mind. So we're looking at it, and the code requires a minimum of 2. We've kind of looked at that earlier, and that was found in 210.11 C1. They required at least 2. Well, what did our dwelling have? Remember, I'm testing your memory here. Again, reading comprehension is what people struggle with. So I want to make sure that we're testing our memory. Remember, there was 4 of them, right? So here in the lesson here, you see that it actually tells you 220.52a tells you the VA per small appliance branch circuit. And here it shows you the reference where it tells you how many you have to have. Now, we've got 4 of them. Remember, you're required to have at least 2, okay? So let's go by the numbers here. Let's paint by the numbers. So small appliance branch circuits must be included when calculating a dwelling unit service. 220.52a dictates that. There's your chevrons. You want to take it the time, go in your code book, go look at 220.52a, read it, and a lot of this stuff will start making sense. And that's what we call the training approach to going from the course material to the code book. Course material to the code book. It's going to make you a much better proficient electrician, and it's really going to help you on an exam, right? So there we go. That's what you do. And so here, B, I'll take this off. B says that it's 1500 VA per small appliance branch circuit. Okay, so that's what it says in 220.52a. You should have just read that if you paused and went and looked it up. So we have 4 of them, remember? We have 4 small appliances in our layout. So that is 1500 times 4. So that is 6,000 VA. So under small appliance, I'm just going to write SA. In the previous one, we wrote GL for general lighting and receptacle. So that is 6,000. So I'm going to write 6,000 down. All right, and that is my small appliance. And remember, we're going to still do some demands here, but you want to write this down. So that's 6,000. Okay. And the next, remember that we're required to have at least 2. And that is where it says it in 210.11c1. Now, do you see why this Fast Tracks course is so thorough? Because we're constantly reminding you of what code sections remind you of how many do you have to have? What's the minimum? All these things get hammered into your head. And we do this all throughout our Fast Tracks program. Okay. So there you go. You know you have to have a minimum of 2, but we've got 4. So we know we're good to go with. We've already done the math right here. And then D kind of reminds you that these loads will be included with that general lighting we just did, and we'll be able to apply some demand factors using table 220.42 a little bit later here in a minute, okay? Some notes to be aware of. An individual branch circuit for refrigeration equipment, and that is permitted in 220.52b1, exception number 2, can be excluded from this calculation, okay? So 220.52a, so those are separate. You're not going to add that into this small appliance branch circuit calculation, all right? So again, those can be excluded away because that is an individual branch circuit for that application. So just kind of keep that in mind. And it says if a dwelling has more than 1 feeder, a separate load calculation is needed for each. It is not necessary to include the step if the feeder does not supply small appliance branch circuits. A load calculation for feeder supplying small appliance branch circuits must include at least 1500 VA for each 2-wire circuit. Okay, so if I have a dwelling unit and it's being fed by more than 1 feeder, and the separate feeder does not supply any of these small appliance circuits, then I don't have to figure those in for that feeder. I've already figured them in for the other ones, okay? So just kind of keep that in mind. I don't have to do it twice. So when I'm doing the load calculation, I do it once, that type of scenario, okay? All right, so that laundry circuit. When it comes to the laundry circuit, it is, again, we look at our form here, and 220.52b, and that's what's going to tell you the VA that you use, and we already know that that's going to be 1500 VA. Now, if you remember, we had 2 laundry circuits in this dwelling that we're working on, all right, but you have to have at least 1, and that's what it states right here. And that tells you that in 210.11c2. Again, those chevrons, you want to go check that out. But you notice it's also in the step. So if you follow the steps in our form, it's going to all make sense. All right, so there's 2 of them at 1500 VA each. So that's 3000 VA. So when I'm going to go down here and write laundry, I'm going to put 3000 VA. And that is my contribution for the laundry. Okay. Now, again, we're going to be able to add this to the laundry, and we're going to be able to, we're going to add this to the general lighting and general use, and we're going to add this to the small appliance so that we can do some demands on this, okay? But we had to get all that information before we could do any demands, okay? All right, now, here's where we're going to introduce table 220.42. So let's kind of go look at that in the National Electrical Code first so we can get familiar with this demand factor table so we kind of understand what this thing is all about. So let's kind of go look at it really quickly. So here's what it looks like, and I'm going to blow this up for you. So we're going to be working on the top one, and this is dealing with dwelling units. Now, I'll remind you, this also applies to multifamily dwellings as well. So that's why it's plural, dwelling units, but it most indeed applies to a individual dwelling unit. And notice what this says is, when you're doing this calculation, and we're going to take together the general lighting and general use receptacle value, we're going to take the small appliance value, and we're going to take the laundry value, and we're going to combine all of them, and we're going to apply some demand factors to it. And we're going to come out with a number that is less than what we call the connected load. So the connected load is just adding all those things up like we did. The calculated or the demand load is the value that we're going to get after we apply some type of allowance in demands for the National Electrical Code. Make sense? So as you can see here, it's telling me the first 3,000 is going to be at 100%. So at least 3,000 is kept at 3,000. And then it says from 3,001 to 120,000, or as we like to say, the next 117,000 over 3,000 is going to be at 35%. And then everything over 120 is going to be at 25%. Now, you are rarely going to have a dwelling unit that's going to be over 120,000, okay, VA. But you might have a multifamily building that you would be over that. So again, you have to understand how to apply this table, okay? All right, so that's it for that. So kind of get the gist of it. Let's get back to our lesson. Now, if you have your form, it's going to look like this on the screen, and you're going to have a 4, a 5, 6, 7, 8, and it's all going to make sense when you figure out. This might look confusing, but it's not. So the first thing we did is we take line 4, right, which is right here, and we're going to add up the totals that we got from our general lighting, which was in line 1, our small appliance was in line 2 of our form, and line 3 was our laundry. So we're going to add all those values up. Do you remember what those values were? Sure, it was 5,565 for the general lighting, it was 6,000 for the small appliance, and it was 3,000 for the laundry. So we're going to add all those together. So I'm going to get my calculator out. I'm going to do 5,565 plus 6,000 plus 3,000. That is 14,565. So that's the number that we're going to be working with. So as you can see right here on the form, that has been plugged in right here. Now, next thing we're going to do is remember what it said. The first 3,000 of that value at 100%. So the easiest thing to do is to take that 14,565 and subtract 3,000 away from it and set the 3,000 aside because you're going to be adding that back later. So set it aside because you need to take that 3,000 at 100%. So all we're doing is take it away, set it to the side, and let's work with the remaining value. So the remaining value is 11,565, which is, again, where it's 3,000, taking the 14,565, take the 3,000 away, and that's where the 11,565 comes from. Right? Now, that is the value that is the 3,001 up to 120. So here we're going to, if it's 117,000 or less, and it is, then we're going to apply what? 35% to that. So it's telling you to take this number and dump it in line 8 if it is 117,000 or less. Makes sense? It's going to fall in that second one where we're dealing with 35%, which is 3,001 to 117. Okay? Oh, excuse me, 3,001 to 120, which is mathematically 117,000. Okay? So we write that down right here. And we do that times what? 35%, because that's when you're dealing with 3,001 through 120. That's going to be multiplied by 35%. So we're going to do it. Make sure we're right here. There's 11,565 multiply that by 35%, and that should be 4,047.7. Remember the rules for rounding in calculations is if it's 0.5 or greater, we're going to round up. So in this case, it would be 4,048, and that's the value that we have right here. Now, that is huge, right? You just went from a value that was 14,000, now you're down to 4,048, but you're not done. Remember? We have to do what? We now have to take that value and add the 3,000 back to it. So you thought you're done. You're not done yet. We have a few more little steps that we need to do. And here's where you get to line 9. Line 9 on our form brings back that 3,000, and then you add, okay, that value right here from line 7, okay? And line 7 was skipped because we didn't have anything in line 7, and I'll show you that really quickly. Line 7 would have been any value that would have been over 120,000. We didn't have any, so we don't have to add that. So here we're simply taking our 3,000, and then we're taking line 8, and it's 4,048. We're adding the two together, and that is 7,048. So guess what? That's the first part that covers our small appliance, our laundry, our general use and general lighting. It went from 14,000, I don't know, what was the total value? 14,000, was it 565? Yeah, 14,565. It dropped it all the way down to 7,048, okay? Half, if you will. That is some serious diversity. Okay, not everything's on at the same time. Not every receptacle is being used. Not all small appliances are being used at the same time. So again, there we go. So write that down. So that's the first major component you're going to need for your service calculation. Okay, so you write that down, 7,048. Now, another thing that I'll remind you, this is the value you're going to use for your neutral calculation because all the things that we just did are 120 volt loads. And we were able to apply this demand factor to those ungrounded hots. We can certainly apply those same demand factors to the neutral. So at this point, forget everything else for the neutral contribution. And remember to put a little N beside this 7,048 because that is all neutral contribution. Okay? So not only is it being used for our load calc, but it's also our neutral value that we're going to be used in our calculation for the neutral conductor. Right? So I'm just going to put a little N beside that to remind me. All right, let's move on. You're doing great. All right, so the next is we're going to move on to the fastened in place appliances. Now, in our case, we had dishwasher, we had water heater, we had disposer, we had trash compactors, and we had attic fans. We had 3 of them, remember? So we're going to kind of bring all those things together, and in the form makes it easy for us to do that because all of those things are considered fastened in place. All right. So obviously A is reminding you of that. And we're going to be using 220.53 because now we're going to be looking to see if we can get any demands for this. Okay. So the first thing we have to think of is, okay, well, remember earlier when I told you to go on and do the calculation for each one of those attic fans? The reason I was doing that is because I wanted to see whether or not they could be utilized in counting the number of appliances. And the answer to that is, well, if they're 500 VA or 500 watts or greater, then they can be. If they're 1/4 of a horsepower or greater, they can be. If they're less than that, then they can't be used here when it comes to applying any demands for that. But you still have to count for those loads. So keep that in mind that you might have a load that you have to take into consideration, but you wouldn't be able to use them as far as getting a reduction in demand for fixed in place appliances or fastened in place appliances. That makes sense? All right, so let's go on real quickly and show you why I wanted to do that. If we go look at appliances for the dwelling unit, and I will do this real quick and we'll go to the code. So you notice what it says here for appliances in dwelling units, 220.53. it says, it shall be permissible to apply a demand factor of 75% of the nameplate rating load of 4 or more appliances rated a quarter horsepower or greater, or 500 watts or greater, that are fastened in place and that are served by the same feeder or service in the one family, two family, or multifamily dwelling. Well, obviously for ours, they're going to be served by the same service. Okay. It says these demand factors shall not apply to, in other words, when you're picking these appliances, don't pick electric cooking equipment, don't pick clothes dryers, don't pick space heating equipment, and don't pick air conditioning, because they've got their own rules they have to follow. These would be other things that we followed, right? Our water heater, our waste disposer, our dishwasher, our trash compactor, our attic fans. And the reason I had you do those attic fans is because I needed to make sure that they were at least 500 VA, or remember, watts and VA are equivalent. I had to see whether or not we could include those in our appliance count. Now, what does it mean by the count? Well, remember, the only way we get to apply this 75% demand is if we have 4 or more appliances. Okay, so we need the 4. Now, what if we don't have 4 or more? What if we have 3 or less? Then we just don't get to apply 75. We still take it at its nameplate, and we have to add it to the contribution for the appliances. We just don't get to apply a demand to it. That's the only difference. So right now, I'm trying to see if I can apply a demand. I think we have at least 4, so we're good to go with the 75%. But I just wanted to kind of walk you through that. All right, so here we're looking at it, and if you look at the form here, and we already converted everything to VA, that's why we did it first. So as you see on the screen, they're doing it now. They're saying, okay, we need to convert that motor, which was 9.8 amperes. We multiply it by the voltage, and that's where we got the 1127 for the disposer. We've already kind of done that. So that's D, that's right here, this disposer. The dishwasher, which is C, we've already done that, which is the voltage times the amps. We did that. That's where we got the 1200. The water heater face value, it was 4.5 kW. So we know that's 4,500. At this point, it's easier to go in and convert it into VA. So it's 4,500 VA. The trash compactor, we already did that. I believe we did that. And that is the volts times the amps. That was 900 VA. We've already done that. And the 3 attic fans, since they're all the same, and we already know now that they qualify to be added here, then it's simply just adding all 3 of them up like we did before, and that was 1,512 VA, and that's what we got right here. So together, how many fastened in place appliances do we have? Well, 3, 4, 5, 6, 7. Well, 7 is 4 or more, so we get to apply 75% demand to that, right? So we simply add them all up, and then we multiply that by 75%. So we're going to check our math, make sure we're right here. But so that's 4,500 plus 1,200 plus 1,127 plus 900 plus 1,512. And that is 9,239. Now, we get to apply that 75%. So we're going to take this value and multiply that by 75%. And that gives us 6,929.25. Remember, 0.25, we can drop it off. And at this point, it's what? 6,929. So that is your fixed or fastened in place appliance contribution. So that's your next value that you write down, and we're going to write 6,929, and that is my appliance. Now, while you're here, let's go on and get the neutral contribution. Now, of all of these loads here, the only one that doesn't have a neutral is the water heater. So we're going to add up the totals again, but we're going to leave off the water heater. So we're going to redo this. We're going to do the 1,200 plus the 1127 plus the 900 plus the 1512, and that is 4,739. So I'm going to write that out to the side, 4,739. Now, We also look at it and say, do we have 4 or more appliances, even with the neutral? And the answer is yes. We have a dishwasher, we have a disposer, we have a compactor, and we have 3 attic fans. So we still have this value that is 4 or more. So what do we get to do? We get to take that value and we get to multiply that by 75%. Remember, if it's good for the hots, it's good for the neutral as well. So I get to apply that 75%. So I'm going to take that 4,739 and I'm going to multiply that by 75%. And that gives me 3,554.25. I can drop the 0.25. So that is my neutral contribution, which is 3,554 for the neutral. Okay? Does it make sense? If it was good for the hot, it's good for the neutral. Okay? So double check your math again. Again, I always harp on this. 1,200 plus 1,127 plus 900 plus 1,512 equals 4,739 times 75%. That is 3,554.25. Drop the 0.25. So that is 3,554. That's the neutral. So put that to the side and put a little in beside it so that you don't have to do it later. It's already been done for you. Okay? But the number that you need for your service load calculation was 6,929. Okay? All right. If that's confusing, then you didn't write this stuff down as we went through it. And that is a problem. You need to be writing things down and following along and getting your scratch paper. It's the only way you're going to learn this process, okay? All right, so notice here that if you have 1, 2, or 3 fastened in place, you don't get any derating. You just take it at full value. You don't get a break on that, okay? All right. All right. We wrote that down, so let's move on now to the clothes dryer. Now, we kind of already did this earlier. Remember, we talked about it. We said that 220.54, here's your chevrons, okay? Here's your chevrons. Stop and go look at 220.54. You remember it was 5,000 VA or the nameplate, whichever was greater, because we are doing the standard method. So in our case, it was 5.5 kW, which is equivalent to 5.5 kVA, which is equivalent to 5,500 watts. But more importantly, it's also equivalent to what we like to work in, which is VA. So that's 5,500 VA for volt amperes. Okay, so that is your contribution right there, point blank, right? Because it is greater than 5,000, so that's what we're going to be using. All right, so you're going to write the next value you're going to write down is 5,500 VA. So at this point, you should have 3 values. You should have 7,048 for the general lighting, 6,929, that's for your appliances. You have 5,500, that's for your clothes dryer. Now remember, you only add this value if there is a clothes dryer in your equation. If you get an exam question and they do not tell you that there's a clothes dryer, don't just assume 5,000 and work that in. You're going to be wrong. In the real world, if there's a clothes dryer, you figure it in. On an exam, if they don't tell you there's a clothes dryer, don't assume that there's one and don't add it to the calculation. Don't fall into that little pitfall, right? You're not required to have a clothes dryer, okay? Just want to make sure you understand that because I don't want anybody to make a mistake in some of these crucial calculations. All right, so we're going to use that. Now, while we're at it, let's go on and get the neutral. Why do we get a neutral for the clothes dryer? Because you're probably all familiar that you have 2 hots, a neutral, and an equipment ground, 4 conductors that run to a clothes dryer. And so what do we have a neutral for? Well, you might have the timer or it might have something to do with the electronics of it. Or some component in that clothes dryer might be 240 for the drum or the heater, and the drum motor might be 120. At any rate, that's what you've got. That's why your dryers have 4 conductors. It's a 4 plug, four attachment plug with 4 prongs on it. There is neutral. And so if you go look at 220.61b, and you can pause this video, go look at it. And of course, in our Fast Tracks program, we tell you right here, go look at it. And what that's going to tell you is for cooking appliances, for clothes dryers, you can take an additional demand of 70% for the neutral, right? So how do you do this? Well, since it's 5,500 for the hots, okay, for our service load calculation, then all we do is take that value and we multiply that by 70%. And that's our neutral contribution. Pretty straightforward, right? So we take that 5,500 times 70%. That's 3,850. So right next to that 5,500, put in 3,850 and then put a little in beside it. That's your neutral. Okay, so we've already done the math on that one. Okay, now if you want to see where that is in the code, I'll take you there because again, sometimes people get lost in it, so we want to make sure that everybody's clear. So notice that it's in right here. I'll show you. It's in part 3 right here. Okay, so we're doing a neutral code calculation. And since it's in part 3, that's why we have to use the standard method to calculate a neutral. Even if we were doing the optional method, we still have to know how to do the calculation under the standard method to determine the size of the neutral. Now, some people don't know how to do all that, so they just make the neutral conductor the same size as their hot conductors and they just move on their merry way. And that usually means because they don't know how to do the calculation that you're doing right now. So let's kind of go look at it, 220.61. And here's where we're at. So this is the basic calculation, and this is giving you the permission, okay? And we're here at the permitted reduction, and we're going to be using right here, B1. And it says, a service or feeder supplying the following loads shall be permitted to have an additional demand factor of 70% applied in the amount for 220.61B1 or a portion of the amount in 220.61B2. All right, so we're dealing with B1, and right here it says a feeder or service supplying household electric ranges, counter-mounted cooking units, counter-mounted wall-mounted ovens, or electric dryers where the maximum unbalanced load has been determined, and we have calculated that out at 5,500 VA for our case, then we're allowed to apply that 70%. Okay, so that's where we did the 5,500 times 70%, and that's how we got 3,850. And that's the neutral contribution. Do it now, it saves you time later, okay? And I already know for everybody that hates the fact that I always say, okay, I can't help it. So if you don't like it, don't watch my videos. If there's any idiosyncrasy that I do that you don't like, don't watch my video. I'm not changing my style for anybody out there that don't like it, okay? So that's my only negative thing I'll say is sometimes I get really stupid comments about little things that's just the nuances that I have as a teacher. I can't help it. Also, I'm redundant as hell. And the reason I do that is because I use a teaching style called redundancy, is where I go over important things to try to help hammer it in your head. And I've developed that teaching style and I can't get rid of it. It is what it is. And if my videos are too long for you or whatever, don't watch. You won't break my feelings. You won't hurt my feelings. Trust me. Okay? Nobody's twisting your arm. But I'm hoping you're getting something out of it. All right, so that's what we do. So now we've done the neutral and we've done the hots, so we're good to go, okay? All right, the next thing we're going to be tackling is that cooking equipment here, all right? So now let's look at so we're in 12 in our form, all right? So our household cooking is over 1750. That's what it says in 220.55, so we get to use the table. Obviously, we had a 6 kW and a 7 kW, if you remember. That's what we were working with. So we most certainly are going to be working out of table 220.55, all right? So, and we're going to go look at the table because I want to show you all these little nuances that are involved here. I get excited when it comes to cooking equipment because I do educational programs just on cooking so that you understand how to use those tables. So let's kind of look at this. Now, I'm also going to tell you that since these cooking appliances do utilize a neutral, we're going to be doing the same thing we did with the dryers when we come up with the final value. We're going to be doing the same thing for the neutral to save us some time. It can apply that 70% to it as well. So just keep that in mind. We're going to be doing that. All right, so and that reminds you that right here. Okay, so we just remind you, and the fast tracks literally is that detailed. If you slow down and you follow it, you cannot go wrong in our program. We walk you from the beginning, okay? From placement, receptacle locations, all the way up to swimming pool applications. We hold your hand because it's important that we teach you these different components. And we're gonna test you on it at the end of every unit. So we're gonna make sure that you walk away knowing it. So let's kind of see where this value came from. So remember, we have a 7 kW counter-mounted cooking cooktop, and we had a 6 kW wall-mounted oven. Now, remember what I said earlier? Both of these fall under column B, right? 3.5 through 8 3/4. They all fall right there in column B. But they also fall under column C because they're not over 12 kW. So now would be a good time to go look and see what's going on when it comes to the table. So we're going to go look at that. Let me go on and get that fired up over here, and we'll go look at it. Okay. So here's what we've got right here. Now, notice this up here at the top, and it may be hard for you to read, so I'll read it to you. It states that Table 220.55, demand factors and loads for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances over 1 3/4. So that's where we got that 1,750 watts. Okay, so that's the same as 1 3/4 rating. And then also it says, in parentheses here, and this is the most important part to me, it says column C to be used in all cases except as otherwise permitted in note 3. So why are we going to be looking at not using column C straight away and just taking that? Why are we going to be able to use column B for this application? Because these two appliances, cooking appliances, fall within the range of column B. Well, you got to go down here to the notes. And if you get down here to the notes, note 3 right here says for over 1 3/4 through 8 3/4, which our cooking appliances do fall, it says in lieu of the method provided in column C, and in lieu of is just fancy language for as a replacement to column C. You can look at column A or column B. It says it shall be permissible to add the nameplate ratings of all appliances, all household cooking appliances rated more than 1 3/4 and not more than 8 3/4, and multiply the sum by the demand factor specified in column C or column B for a given number of appliances. Okay, it says where the ratings of the cooking appliance fall under column A and column B, then you do each one separately and then you add them together. Okay, so let me kind of translate that because that sounds kind of like, what is that, secret code word language. Okay, no. So if I had an appliance that was 6 kW, right? And I had an appliance that was 3 kW, okay? Then 3 kW one, I'd use column A. The 6 kW one, I would use column B. So if, in this case, let's say my cooktop was 3 kVA and my in-wall mounted oven was 6 kVA, then the 3 kVA would be one appliance times 80%, and you write that down. And then the other would be the 6 kW or kVA times 80%. You write that down and you add the two together, right? And that would be the value that you would use, okay? And that would be permitted to do that. Now, in our case, we're all under B. So we have two appliances under B. We have one 6 kW and we have one 7 kW. So adding them two together is 6 plus 7 equals 13 kW. So we have two appliances, okay? And we got here, and we have a multiplier right here as 65%. So I get to take that 13 kW and I get to multiply that by 65%. And what is that going to give you? That is going to be 8.45 kW, which is equal to 8,450 watts. right? Or 8,450 VA. Now, you still want to compare that to column C. And in column C, what is the value in column C? Well, in column C, I have 2 appliances. And under column C, it says to use 11 kW. Well, the in lieu of that we read earlier in note 3 says that in lieu of the value in column C, I'm going to let you use the lesser value that we calculated in column B. So I'm going to get to use 8,450 in my equation. I don't have to use the 11. That is what the in lieu of means. And that is very unique to range applications. Okay. So again, we're talking services. We're not talking individual branch circuits. I have a totally separate video for that. Check that out, where you would combine the two and treat as a single range. That's not what we're doing. Okay, we're doing load calculations at this point for the service or feeder calculation. All right, so we'll go back to our equation. And that is where we got the 8,450. Now, so you're going to write that down. That is the contribution for our cooking, 8,450 VA. Now, while we're here, remember the 220.61B? Let's get that neutral contribution while we're here. So I'm going to take that 8,450, multiply that by 70%. So that's 8,450 times 70%. And let's see, 8,450 times 70%. That is 5,915 VA. And that is my neutral contribution. Okay. Again, always check your math. 8,450 times 70%. And it is 59.15. Okay, write that down, put a little in beside it so you don't have to redo that again later. You're done. Okay. All right, next we're going to come to that line 13 in our form, and that is AC or air conditioning. Now, again, we're going to look to see with these, remember we said ours, we're going to be treating these as a non-coincident load. And what that means is that when one is running, the other one can't run. So they're either thermostatically controlled, they're interlocked, so one can't be on with the other. But you need to keep in mind that if you're dealing with something like a heat pump with heat strips and things like that, there are other rules that you've got to follow, and you need to take the nameplates for the heat pump and take all those things into consideration. Now, with an optional method, there's other things that we can do, but we're doing the standard method. So we do not have the ability to discount anything if they're not non-coincident loads. And again, non-coincident means that the heat or the AC will not be operating at the same time, okay? So it might have some thermostatic control or some interlock. Now, I do want to remind you that in the real world, if you're not doing a one-family dwelling, you're doing even a commercial building and you're using the standard method, non-coincident loads don't just have to be AC versus heat. It can be any application where you have AC or heating where there is a situation where you have 2 motors and one can't come on while the other one's running. And you get to take the larger of the 2, okay? Because obviously you size everything for the larger, then the one that's the smaller is running, it's not going to it's not going to hurt anything because you sized everything for the larger. So that's what that means by the non-coincident load. Now, in the 2020 National Electrical Code, there's a little step you have to do when we're comparing heat versus AC. And so we're going to cover that. Now, in the 2017 code, you just take the heat versus AC. You don't have to get complicated. But when you're doing the standard method in the 2020, then you have to do a calculation to determine which one's the larger. And then if the one that's the lesser happens to also include the largest motor in the dwelling, then you need to take that motor at 125% and then redo the math again. And if now the one with the lesser becomes the greater, then you're going to use that value. If it doesn't become the greater, then you just discount the lesser and you go with the greater. Does that sound confusing? Well, let me tell you, 220.60 can be quite freaking confusing, and it's caused quite a bit of confusion for folks, but that's the best way that I can explain it. So let's kind of work this equation here. All right, so the smaller of the 2 of the non-coincident loads can be omitted as long as they are never energized simultaneously. Okay, remember, If there's a chance that they could be both energized at the same time, then you don't do that. You have to count for both loads, okay? This is only coming into play here in 220.60 only comes into play if there's a non-coincident load issue, okay? Now, by definition, non-coincident means not occurring at the same time. A dwelling's electric heating system and air conditioning system may be non-coincident loads, but that's an important maybe because they may not be. For example, baseboard heats and central air. They could be ran at the same time. So 220.60 is not going to come into play, and you're simply going to take your value for your heating and you're going to take your value for your air conditioning and you're going to run with it. Okay? You're not going to get to apply any non-coincident load application in 220.60. So don't overcomplicate it. You either can use 220.60 or you don't. Okay? All right. So in our case, we did our math earlier because we were very diligent. And we know that we needed to get the value for that air handler because that's going to be used for both in our case. So that was 368 VA, which is 3.2 times 115. We already did that. And then since both are going to be used for both the heating and the air conditioning, we need to blow that air around. So when we're comparing the two, we want to make sure that we add that air handler to both when we're comparing everything. All right. So remember our heat. So our heat was 3 banks of 5,000. And so maybe that is strips of heat in a heating element that's next to a central air conditioning system. So it's still going to blow the air. It's going to heat the air that's blown through the ducting system, but it's not part of a heat pump. It's not worked into it. It's separate, okay? So it's 15 kW, which was the heat, plus we got to add that 368 VA into the equation for that air handler, giving us 15,368. Now, we're using that right here in this value, okay? Right here. So we haven't done the air conditioning math yet. We're assuming the heat's going to be greater, but I can tell you by looking at it, 15,368 is probably going to eclipse the air conditioning. Because you guys remember earlier, the air conditioning compressor was 3818, the air handler is 368, and the condensing fan was only 230. Nowhere near, okay? Nowhere near the heat. So, but remember that little exercise I told you have to do in the 2020 edition? We're going to do that exercise. So up front, the heat is greater. So the air conditioning is the lesser of the two non-coincident loads, correct? So when you read 220.60, it says if the non-coincident of the lesser of the two, which in this case was the AC, if it happens to have the largest motor in the building, then you redo that calculation and you take that motor, that air conditioning compressor at 125%, and then you take 100% of the other loads that are associated with the AC, and now you compare that against the heat again. And if it happens to overtake the heat, then you use the air conditioning. If it still falls short and not greater than the heat, then you just get rid of it. Throw it away. Because obviously if you're using the heat, then you're going to obviously have the air conditioning covered when it's running because it's less than the heat. So you're sizing everything for the heat. So where's the problem? There is no problem. In fact, our heat is probably 3 times greater than the AC in this case. But anyway, let's do the math and to make ourselves feel a little better here. So here you go. So remember that air conditioning unit was 16.6 times 230, and that's where we came up with 3,818. Well, we need to do that again because it is the lesser of the two compared loads. So I'm going to take that 16.6 times 230 times 1.25, and that's going to be 4,772.5. Remember the 0.5, we're rounding it to 4,773. And then, of course, we add the other associated loads, which is the air handler. So we took that value, so 4,773 plus, what did we get? We had 230 for the condensing fan, or the condenser fan, so plus 230. And then, of course, we had the air handler, that blower motor, and that was 368. So let's add that to it as well. That's 5,371, I believe. And I think they have 5,271. So let me check my math again in case we have an error here. So 4773, because it could be me, right? So I'm going to add that. And I'm going to add 230. And I'm going to add the 368. And theirs is an error. So they have 5271. I believe that it's supposed to be 5371. Okay, I'm going to make sure, just one more time. 4773 plus 230 plus 368. 5371. So there's an error here in the material. And again, no author of a publication is perfect. Okay, now in our case, it's not going to matter because this is only a third of what the heat is anyway. So we're going to discount this anywho. But this is important because since we're not going to be using the motor, which is the largest motor at 125%, we still are going to have one more step where we have to go hunt for the next largest motor in order to capture that additional 25% that's required for the largest motor in the building. Okay, but we don't use the air conditioning because we just got rid of the air conditioning. We're using the heat, okay? So that's the reason we have 15,368. Make sense? All right, so we're going to write that down. 15,368. That is our contribution for there as well. Now, while we're here, we might as well get all of our neutral contributions, okay? Now, here's where it gets interesting. Because our neutral contributions that are being added into this equation, there are certain appliances that are going to have neutral loads and certain that aren't. And now, even though we're comparing AC versus heat, all of these are going to be running at some point. So they do add neutral contribution. So here, when it comes to the neutral, we want to look at the air conditioning loads that are 120 volt, and we want to look at any heating loads that are 120 volt. Well, the heat strips are not. They're 230, 240, so we don't have to worry about those. But remember that air handler? That is a situation. Now, what about that air conditioning compressor? Well, that's not. That's 230 or 240. That doesn't have a neutral load. So the only thing that we need to write down real quick here for our neutrals is that air handler and that condensing fan, right? We need to add those neutral contributions. So that was 230. So I'm going to write 230 down. And I'm also going to write the 368. So I'm going to add those together. So 230 plus 368, and that is 598. So I'm going to write that down and put a little N beside it. That's my neutral contribution for my AC and heat. Okay? All right. Next is the one that causes confusion to everybody, and they want the code to just say this in black and white. The largest motor. So you have to hunt for the largest motor. Now, in the previous exercise, if the AC at the 125% for the air conditioning condenser, if that happened to be the largest motor and that happened to be the one that won in the comparison, then we wouldn't need to do this because we're already accounting for that 25% for the largest motor. But since we got rid of the AC and we use the heat, now we have to find that largest motor. Now, where do we get this rule? This rule is in 220.50, but it makes reference to 430.24. And that rule says for motors, you take the largest motor at 125% and the sum of all the other motors, and the sum being the FLC of all these other motors. Well, in this case, we look for the largest motor, which we've already taken at 100%, even if we have applied some demand factors, let's say for appliances, even though we applied that 75%, we started out with this value at 100% when we did that math. So now we need to go searching for the next largest motor because now we can't use the AC because we got rid of that in the comparison in the previous line. So what's the next largest motor? Well, if you look at your numbers, you'll see that the next largest is going to be the garbage disposer, and that was at 1127 VA, okay? All right? So each one of those attic fans, well, they were only 500 each. The trash compactor was only 900. So in our case, the largest logical motor that we're going to be dealing with is the disposer. Now, some people will say, why don't you choose the dishwasher? Now, in the real world, if you want to, that's fine, but that's not really a motor. The way that nameplate is listed, that's more an appliance. So we're looking for the largest motor that we're going to apply under this rule in 220.50. So in that case, it's ones that give us a horsepower value or horsepower rating, and we had to kind of do that calculation. So in our case, the disposer, that's what we're looking at. Okay, so that was 1127. So we simply take the 1127, and remember, all we're trying to do is capture that additional 25%. Because we already took the trash compactor, the in-sink waste disposer, we already took that at 100%. We're only trying to capture that additional 25% to meet 220.50, right? So we take that 1125, we multiply that by 25%, and that's where we get 282, and you're gonna write that down. That's that additional contribution. So again, I'm gonna write that down as 282, okay? Now, as far as the neutral is concerned, you need to account for that in your neutral as well. That is your 25% contribution for the neutral. Same thing. Again, see how the rules kind of mirror each other? So I'm going to write that down to the side as my neutral, 282, and then put an N around it for the neutral. That way we don't have to do it later. All right? Okay. Now, the value will equal 281.75 in your math, which again, using the rounding rules, that's how we got 282, in case you wondered how we did that rounding. All right, let's move on. All right. Now, you're going to add up all of those that we did, and we're going to see if this number is correct. So get your calculator. You've done it with me. So the first one was that 7,048. That was the general lighting and general use, plus 6,929. That was our value for our fixed or fastened in place appliances. So 6,929 plus 5,500 for our clothes dryer. So 5,500 plus the cooking. If you remember, that was 8,450. So we're going to add 8,450 plus the heating load at 15,368, so we add that down, 15,368, plus that 25% for the largest motor that we calculated, which is 282. So we're adding 282. And that should be 43,577. So you see the author got it right here. So you know what? He got it a little wrong in the math, but it happens. But he corrected himself here at the end. No harm, no foul. And you're going to do that as well. You're going to find out that you miss a few things. But again, practice makes perfect. Now on our form, this is where you start punching things in. So right here, you're going to be applying the total calculated load, and that was 43,577. Again, right here, 43,577. Plugging that in right here. And then we're talking about the voltage of the system. Now, here is where you're going to use nominal voltages, like 240. And so it's 43,577 divided by 240. So let's do that. 43,577, divide that by 240, your volts, and that is 181,000.57. Guess what? Amps, we're going to be able to do what? We're going to be able to round those. That's what it says in 220.5b, that we can go 0.5 or greater, we round up. If it's less than 0.5, we can drop off. And so, because we're dealing with amps, so we're able to do that. So in this case, we round that 1.8157, we round it to 182, and that's what we have right here. So this is your minimum ampacity when it comes to conductors. So I have to have conductors that can handle 182 amps, okay? Now, we need to size the service at this point. So what we're going to do is we're going to go to 240.6, and we're going to look at the overcurrent protected devices that we need to have for this service, okay? And we need to know this because we're going to be able to do something here in a minute when it's sizing the conductors. But first of all, I just like to throw the premise out there. Looks like we have to have conductors that can handle 182 amps. Okay, we haven't done anything yet. Bear with me. Now, using that 182, we have to find overcurrent protection that can protect it at 182. Okay, so let's go to the code, and I'm going to 240.6a. Now, in our program, you're going to notice these things because in here, we've got these little, if you look over here, you can see right here, oops, let me get rid of this. You can see right here that we actually put it in here. See, 240.6a? All of this walks you through it, step by step, to the point where you get so smooth at this that you've become an expert at sizing any dwelling. As long as you can work it piece by piece, you can solve anything you want. All right, so let's kind of go to the code. And we're looking at circuit breakers or fuses here. These are standard values. And remember, 182, we go here and we notice that it doesn't correspond, okay? And if it doesn't correspond and it's less than 800 amps or less, then we go to the next size. Where do we get that allowance? Okay, well, we get that allowance in 240.4 that tells us if it doesn't correspond, then we can go to the next standard size. So 182 is not here, so we choose this right here, a 200 amp rated. So that is our service rating, okay? That is the breaker's rating, okay? That's what our service rating is at this point, okay? All right, let's come back to the exercise. So we did this to size the service to get that 200 amps. Well, now we're going to focus on conductor selection, okay? We just started out saying we know we had to have a conductor that's at least 182 amps, but we might be able to be less than this. I'm going to show you why. But we did use this to determine the rating of the service, which is 200. Okay, so here's what we did. We know that the standard doesn't apply to 282, so that's why we went to table 240.6a, okay? All right, everybody's square on that. So let's go a little further. Now, here's where it starts to get confusing for a lot of people. I could size these service conductors if I wanted to at that 182. So if I were to go to 31016 and select a conductor, and I'm going to do that just to kind of show you how this works. If I go to 31016 and use that 182 amps and choose a conductor that protects it, I'm going to go down and I'm going to do that here. So I'm going to bring this table up and then we'll go there. So this is what we're looking at. So I am going to be under the 75 C column, and you might be asking why. That's because in 110.14c, since we're over 100, then we're going to be using the 75 C, okay? And keep it simple. If you want to learn about adjustment and corrections and all those things, I have a video for that called Derating Demystified. You can get access to that in our annual or monthly subscription program over on our website. It's a great video that walks you through conductor sizing and ampacities and all that good stuff. Right here, we're not assuming any adjustment or corrections. We're just sizing conductors based on an exam application. All right, so we would be under 75. Now, if we wanted a conductor that's good for that, that would put us right here because 175 is not enough. We needed 182, so that puts us right here. So it looks like copper, we're going to be a 3/0 copper, okay? And if we were doing aluminum, we're under the 75 as well, and we're going to come down, and it looks like we would need to have a 250 KC mil aluminum in order to handle this 182 amperes, right? If we didn't want to use something I'm getting ready to talk about now, okay? All right, so what am I talking about? All right, so I'm going to take you to 310.12 real quick. So this is 310.12. Our situation is a single family dwelling. The ampacity that we calculated out puts us between 100 and 400 amperes, so we're right in that sweet spot. It is a one family dwelling. We're doing service conductors, okay? There's only one panel, and this panel and these service conductors are seeing 100% of the load, okay? So that means it's going from a weatherhead to a meter to the service disconnecting means, which may or may not be the panel outside with the main breaker, or it might be a disconnect outside that's feeding a panel just inside. However your flavor, Again, that's 230.85 for the emergency disconnect and all those rules, which we're not going to get into. At this point, we're going to assume that these service conductors are seeing 100% of the load we just calculated. Okay? If that's the case, then I am permitted to use 310.12. And so watch how this works. So in this rule, it says, for one-family dwellings and individual dwelling units of a two-family or multifamily dwelling, so for the feeders to those individual dwelling units, I could use this as well if it falls in these parameters. It says, conductors supplied by a single-phase 122/40, and that's what ours is, shall be permitted to be sized in accordance with 310.12a through d. Okay? And again, we're talking what? The conductors, service conductors. We're able to size them in accordance with this, right? See, the service and feeder conductors. All right? Now it says for one-family dwellings and the individual dwelling units of a two-family or multifamily, single-phase feeder conductors consisting of two ungrounded conductors and a neutral. That's like an SEU style, whatever, neutral, from 208Y to 120-volt system shall be permitted to be sized in accordance with 310.12a through C. So this applies also to a three-phase system that is deriving single phase from a three-phase system, where it is a 208/120 system. Then you could use this rule as well. Okay, so let's assume ours is dealing with this is a single-phase, single-family dwelling. It's 122/40. It falls between 100 and 400. This is not an exception, folks. This is an allowance in the code. We can use this. And let's see how this impacts that 182 amps for sizing a conductor. All right. So, and can it still be protected by that 200 amp device? Okay, so let's go back to the lesson. So let's kind of read the lesson and we'll learn. Again, this is line 18 in your form, and it does give you all the references right here so that if you're confused, it's right in the form. That's what I love about these. It says for services rated 100 through 400 amperes, it says the service conductor supplying the entire load associated with the one-family dwelling, or service conductor supplying the entire load associated with an individual dwelling unit, if it's a two-family or a multifamily dwelling. It says it shall be permitted to have an ampacity, and that's of these conductors now, an ampacity not less than 83% of the service rating. Okay? Now, if no adjustment or corrections are required, then you can pull straight from this little table that's found in 310.12. You just pull right from the table. You don't even have to do the math. It's already done for you. However, if there are adjustment and corrections that have to take place due to ambient temperature that's other than 30 degrees Celsius, 86 degrees Fahrenheit, or you have corrections that need to take place for the number of current carrying conductors, and I probably should have said that the other way. Corrections for the ambient, adjustments for the number of current carrying conductors that exceed 3, or that you have, 3 or more, then you're going to have to do that. If that's not in play, then you just simply pull from the table. Pretty simple. And there is a table here, and I'll show you the table real quick. So as long as you don't have any adjustments or any corrections, again, adjustments for the number of current carrying conductors or corrections for the ambient temperature, then you can go right to this table. In our case, the 200 amp right here means it only needs to be a 2-aught copper or a 4-aught aluminum. Huge price of copper today. So you went from a 3-aught down to a 2-aught using this 83% allowance, okay? And it went from a 250 kcmil aluminum down to a 4-aught aluminum, and that's why you probably see a lot of 4-aught SE cable used, service entrance cable used in aluminum. 4-aught is because they're utilizing this allowance in 310.12. Now, if you're in the 2017 code, it's 310.15B7, but it changed in the 2020, 310.12, okay? So that's how you would apply it. So can we just use the table? Absolutely. But how do we apply that if we just want to be guys and gals that don't want to use tables? Okay, because this table is reintroduced in the 2020, but in the 2017, it's back in informative annex. So unless you knew to go there, you had, in formative annex D, by the way, unless you knew to go there, then you had to know how to do the math. So in the math, it's pretty simple. You take 200 times 0.83, and that is 166 amps. So I have to have a conductor that can handle at least 166 amps. So if I were to go to the code, and that's where I'm at, and I were to go to 310.16, and I have to have one that can handle at least, let's see, let me go further here. Let me go a little further. Sometimes Link doesn't want to jump for me, so you gotta do it yourself here. All right, here we go. So let's go here. So for 166 amps, then we have to have a 2-aught. So you see, it met the same as the table. And that's what the table was based on, 83%. Now, when I tell you, if you had to do, let's say, and I'll just show you how this works. If I had to do something based on an ambient temperature, because probably not going to have a number of current carrying conductors, 3 or more. If you're not going to have that, and I'll show you that real quick, just so that we can make sure everybody's clear on that rule. Let me show you where you have the number of current carrying conductors right here. So you have more than 3. Okay, so I don't know why I kept saying 3 or more. It says where you have more than 3 current carrying conductors, you're going to have to do an adjustment. So again, I say it so often. So where you have more than 3, then you're going to have to do this. So here it says the ampacity of each conductor shall be reduced as shown in table 310.15C1, where the number of current carrying conductors in a raceway or cable exceeds 3. Okay, so it's more than 3. All right. Glad we cleared that up, because I know that I was going to get somebody in this video say, Paul, you said 3 or more. That's wrong. Look, I don't edit these. I turn the camera on and I just go. So cut me some slack, okay? At least I get there in the end, all right? So where we have more than 3 current carrying conductors, we're going to have to do it. Now, with the services, even with feeders for 1 and 2 family, things like that, it's probably not going to be a situation where you have more than 3 current carrying conductors, but you could have an ambient. So I want to show you what it means that you can't use this table. Just pick it straight from the table. Now, the reason I say that is if I bring you back here, it reminds you right here. It says no adjustment or correction factors are required, then you can simply pull from the table. But if you do have any adjustment or corrections, then you still can use the 83%, and it has to be at least that, but you got to do a little math. So let me give you an example. Let's say I had conductors that are outside, service conductors, and they're in an area where the ambient temperature, instead of being 86 degrees Fahrenheit, it could be 92 degrees Fahrenheit, okay? So what do you got to do here? So now, since I'm probably dealing with a conductor that's inside of this cable assembly that is rated 90 degrees, okay? So it's probably THHN rated insulated conductors. So I'm allowed to use the 90 value for adjustment and corrective purposes. And it tells us that in 310.15 that we can do that, okay? All right, so I won't go look at that. You either believe me or you don't. So in this case, let's kind of see what we got to do. So first things I want to do is we know that the conductors can't be less than 83% of the service rating, okay? And that was, in our case, 166 amps, okay? Now, I need to find out what the correction value is for that 92 degrees Fahrenheit, because the table deals with 86 degrees Fahrenheit, 30 degrees Celsius. So since something deviates from 310.16, I know that I'm going to have to apply something. So what we're going to do is go back to the code. We need to get a number that we're working with. And again, I go over this in my D-Rating Demystified, so this is going to make this video longer than necessary, and I know that I'm going to get some hate mail from it, because it doesn't matter how much I try to please people, there's always one person out there, and you know who you are, that hates my videos. Okay, so again, sorry about that. It is what it is. You really don't have to watch me if my videos bother you. All right, so here's the ambient table right here. And remember, here we're dealing with 310.15b1 because this correlates to 31016 table dealing with the 30 degrees Celsius. The B2 table here is dealing with 310.18, 310.19, 310.20. Since we're dealing with normal ampacity and using 31016 or even 31017 for what's called open air or free air, we're going to use this table when it comes to the ambient. All right, now, since our conductors have an insulation rating probably of 90 degrees C, we get to use this column. So now we come down here and you notice that the 86 degrees right here is a 1.0, so it's not going to affect our value. That's why it starts and everything's based at 1.0 because that's what meets the table. But we had what? 92 degrees Fahrenheit. So that falls down here from 87 to 95. And this modifier is 0.96. Okay? So remember that. Write down that 0.96. Okay. So now let's go back to the ampacity table and see what we've got to do. All right, so here's our ampacity. All right, so we get to use the 90 for adjustment and corrective purposes. And we come down here, and so what we're going to do is, since we already know the load we want, we have to work with 166. And remember, it can't be less than 83% of the service rating, which is 166, even after an adjustment or correction. So we're going to take that 166 and we're going to divide it by the 0.96 division. We're going to be going up, and then we're going to look for a conductor in the 90, and then we're going to show you how multiplication can validate that for us. So I'm going to take the 166, divide that by 0.92, and that gives me 180.43. Okay, so that's the value that I'm working with. So now I'm going to go to 31016, and I'm going to go to the 90 degree column. And remember, copper, unless stated otherwise. I'm going to go down here, and I need to find a conductor that's good for 180.43 amps. So it looks like right here, a 2-aught. So it looks like we might be okay either way. So we have a 2-aught, which is good for 195 amps. Now, let's make sure that after that adjustment or correction, okay, in this case, we're dealing with a correction because it's dealing with ambience. I'm going to take that 195, and now I'm going to multiply that by 0.96, and that's going to be 187.2. Well, is that 187.2 okay to handle the original 166 that we needed to have? Absolutely it is. So we're still good with that 2-aught. It didn't change anything, okay? So that's how that works. But again, if you want to see that in a lot more detail, then make sure you check out my derating demystified video. It's really a lot of good information, and we spent a lot of time developing that for you. And it's only available to annual and monthly subscribers. So again, if you're perusing the internet here, you're not going to find it. You got to be a member, and we hope you do support us by becoming a member. All right, so that's what we did here. So remember, it's 2-aught or it's a 4-aught. And we went through this exercise right here, right? 75 degrees C, 31016, 200 amps. It was a 3-aught, but since we used 310.12, that's the way we were able to get away with a 2-aught, okay? That's how it works out. Now, with that neutral conductor, right? So we want to remember how we did that. So we already took all of our values. Number one, no neutral conductor is connected to the water heater, so we didn't count the water heater. All fastened in place appliances utilize a grounded conductor have to be included. We already wrote that down. We already added those up. The heat in the AC compressor at 240, so there's no neutral. We don't equate that. If the largest motor is 120 or 115 or whatever, we use that motor in line 14. We did that, and we took that value, the largest motor. That's how we captured that largest motor. And we're doing that and trying to capture the value for the largest motor. For the purpose of the load calculation, terms neutral in the grounded conductor is synonymous, doesn't matter for what we're doing. And we kind of worked all that math. So let's kind of scroll down and see what we did. So if you look at these numbers, let's kind of correlate them to what we did. All right. So when we looked at these total numbers here, so that's 7,048. Remember, that's what we had before. That was our general lighting, our small appliance, and our laundry. We wrote that down as a neutral contribution. Check, we got that. Not a problem. The next thing that we went and worked out was our appliances. Notice we left out the water heater, but we came up with our total value and we applied the 75%. And so the value that we had written down was 3,554 for our neutral, and that's what we see right here, okay? The next one we had our cooking, and remember, we took the cooking, which was 8,450, and we multiplied that by 70%, and that is 5,915. That was right there. Oh, and here's that clothes dryer at 3,850. We did that. We took the 5,500. We multiply that by 70%. That was 3,850. We already did that. We wrote it down. Okay. Now, that air handler at 368, we took that down, and we have to account for the largest motor. Remember, we didn't do that because we were already going down through our list. But here, since the AC was discounted, we still have to go through and see, okay, well, which one of these is the largest motor that we're going to be dealing with in M, right? So M, okay, is a neutral contribution, so we added that in, okay? Let's see. Oh, the largest motor is down here. We already did that. That's the 282. Remember, we added that in. That was the in-sink waste disposer, and we took that extra 25% of that 1127. That's right here, okay, right there. Now, remember that air handler and that air condensing fan? No, we added ours together and came up with 598, but here they're just showing them individually. Doesn't matter. It means the same thing. So those are all of the loads that we worked out. So then all you do is you go down and you add them all up. And just like here, so I'll just do what we did. I'll do 7,048 plus 3,554 plus 3,850 plus 5,915 plus 598 plus 282, and it is 21,247, the same as you see here on the screen. Now, the beautiful thing is we already did this while we were doing the load, so we don't have to go back through and do this again, okay? Now, what do? The same as we did before in applying this. We have to take it, and we do what? We simply take it, and we divide it by 240. So I'm going to take this 21,247, divide that by 240, and that's going to give us 88.52, okay? And at 0.52, we round that to 89, and that is going to be the amps that we have. So we need to have a conductor that can handle 89 amperes. And we're going to do that first, okay, to see whether or not what we need as far as size. Because first of all, we have to handle the maximum unbalanced load. And right now it is 89 because we round it. So let's go to the code really quickly. Show you how this works. And we're going to be looking for conductors again right here. And we're under 75 degrees C. And we're going to go down and we need 89 amperes. So it looks like, well, 85 is not going to work. So we need 100 amps right here. So we're going to need a 3 copper. So write that down because I want to show you something. 3 copper. Okay, now if it was aluminum, by the way, and we were picking aluminum, and we go over here, and we still need 89 amps, so we're going to go under the 75. And why are we using 75? Because, again, we're using 110.14. We only use the 90 for adjustment and corrective purposes when we're doing these load calcs. All right, so we're going to go down. And let's see here. So here's 100 amps. So wait a minute. We want to be under the 75. So we needed 9. What do we need? 89? Well, there you go. There's 90. So that would be a 2 gauge. So 3 gauge copper, 2 gauge aluminum would satisfy the need. Now, before you move off of this, we also need to compare this to 250.102C1. And how do we get there? Well, it reminds us in 250.24 to go verify this. And it can't be less than that. It also can't be less than the size of the grounded conductor as well. So, but we want to go ultimately 250.102C1. So we already know that we believe it's going to be 3 copper. Okay, but now let's kind of go in the code and verify that at 250.102C1. So I'm going to go to 250, and I'm going to go to 250, and then I'm going to go all the way down. Oh, by the way, let's show you where it requires that real quick so you say I'm not full of crap. Here it is in 250.24, and you'll get down here in grounded conductor right here. Okay, the grounded conductor neutral right here. It says the grounded conductor shall be installed in accordance with 250.24C1, right? And you get down here, you see sizing, and it ultimately sends you to table 250.102C1, okay? So just so you follow the logic train, it can't be smaller than that. Now, we've already calculated it out to be a 3. So we know that it can't be smaller than what's in this table, 250.102C1, but it also has to handle the load. In our case, the 3-gauge copper is what we need, so we need to compare and make sure that we're in the right track. So let's go to that table. I'll click on it, and here's the table. And here, we're doing it here, and it can't be less than. So here we are, and this is based on the conductor size. So we already determined that in this case, the hot conductors that were being used was a 2-aught copper, remember? So we go down here for 2-aught copper, right here. Okay, we're using the ungrounded conductors for this. So 2-aught copper, and that's why you had to do the calculation under standard method. We had to know what size the ungrounded hots were so that we can apply this here. And so it needed to be at least a 4-gauge copper. Well, a 4-gauge is smaller than a 3-gauge, right? 3 is larger than a 4, 2 is larger than a 3, yada, 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 you get it. So we're okay. That 3 was the right choice. It is not smaller than this here. So ultimately, at the end of the day, our conductors are our hot conductors, a 2-aught copper, and our grounded conductor, or our neutral in this case, is going to be a 3 copper. Okay, now let's finish this all out. What if we have a ground rod? And now we're going to take our grounding electrode conductor down to our ground rods. Okay, so that is 250.52. You find the ground rods. Now, in that application, we're choosing that as our electrode. So 250.52A, and I believe it's A6 or A5. Let me go look. Again, my mind, I teach this all the time, so again, there's other people out there that say, oh, Paul, you didn't remember that? That's okay. You do you, boo. So 250.52, it is 5, yes. So that is ground rods. 8-foot ground rods, okay, and of course the installation requirements are down here under 250.53. They have to be at least 6 feet apart, 8 feet long, 6 feet apart, and you have to install 2 of them unless you can show that one of them is 25 ohms or less than there. Now, when it comes to sizing, the grounding electrode conductor from the panel, from the grounded terminal bus, down to that electrode, we're going to be looking at 250.66 for sizing. Now, I'm going to go to 250.66. Now, here's the table when it comes to sizing the grounding electrode conductors. Now, if you're doing ground rods, you're doing concrete encased electrodes, or many people refer to as a UFER, or you're doing a ground ring, then you can go to what's called 250.66 A, B, or C. But if you're doing a water pipe ground, in-ground steel, metal tanks, any of those that you're allowed to do under 250.52, other than a rod, pipe, or plate, other than a ground ring, or other than a concrete, then you're going to go right to this table. And if, for example, we happen to be using water pipe ground, okay, and you need to size it from the panel to the water pipe ground, you're going to come here. And again, you're going to use the ungrounded conductors. In our case, was a 2-aught. And then it's going to tell you that the grounding electrode conductor to that water pipe, that copper cannot be less than a 4-gauge, okay? However, if you're just doing ground rods, then you can use 250.66A. And let's look at that. So 250.66A is this right here. So the connection to a rod, pipe, or plate, any one of these. If that's the case, it says the grounding electrode conductor or the bonding jumper connected to single or multiple rod, pipe, or plates, or of any combination thereof, as described in 250.52A5 or A7, okay, A7 being the plates, by the way, it says, does not extend onto other types of electrodes that require a larger size conductor. It says the grounding electroconductor shall not be required to be larger than a 6 copper or 4 aluminum. So you get to ignore the table. You can run a 6-gauge copper, and guess what? It wouldn't matter if that panel or that service equipment was 10,000 amps. If it's ground rods, pipes, or plates, and you're going from the panel or service equipment, switchgear, switchboard, if you're going down to that ground rod, and you're not going to go from that ground rod to another electrode that would require a bigger one, like from there to a water pipe, which we saw required a 4. If you're going down to the rods and that's it, then it doesn't need to be larger than a 6. You're done. I know that's sometimes hard for people to grasp, but it doesn't need to be larger. It's fine. Can it be larger? Can engineers specify it to be larger? Absolutely, they could, but it's not required to be. It only needs to be a 6. Can you go beyond code and make it larger? Absolutely. And if you want to use more copper, I work for a company that makes copper conductors, go for it. Okay, Christmas time's a coming and I need a bonus. So feel free to do that. You're just not required to do that, right? But just remember when you can use these and when you got to go to the table, and then you're going to be perfectly fine, okay? All right, so that's pretty straightforward and how that works. So in our case, if it was ground rods, then it only needs to be a 6-gauge copper, boom, and we're done. So 2-aught ungrounded conductors, 2-aught copper, a 3-gauge neutral can handle the maximum balance load. We did that calculation. We're good to go. And then my grounding electroconductor is a 6-gauge, two ground rods that are at least 6 feet apart and 8 feet driven into the earth. Those type of concepts. Okay. So again, and we'll talk about all those nuances in other videos. I do want to remind you that we will be showing all of our videos over on Fast Tracks Tube, like in YouTube, fasttrackstube.com. So make sure you check that out and bookmark it because there's going to be a lot of information there. So let me bring you back to me and end this. This was a really long lesson. And I will remind you that I did not pause. I did not edit it. If I said something, I'm sure I corrected myself. It's a lot for me to spit out. And I am not like most educators where they have to edit things and cut it up. And I don't do that. I don't like to do that. I like to spit it out. And sometimes if I say anything and I get a reference here or there, a little bit wonky, don't hold it against me. I'm trying to do this off of memory and I am rapid firing these things, folks. But usually I pretty much cover myself and I bring it back to where it needs to be. So again, haters will be haters. But hopefully you get something out of it. And hopefully you enjoyed this episode and you learned something from it. If you want to really learn more about the codes and calculations and getting deep into it, if you want to come to our Wednesday night sessions, then do me a favor. Think about visiting electricalcodeacademy.com.net or .org and getting in our Fast Tracks program. I promise you, we will teach you all the calculations you need to know. I am here to answer questions. You can come to Wednesday night. You get access to a special area in the Sparky Hub. I'm here for you, and you're going to get way more than the money you invest in it. You're going to get a lot more of my time, and I'm going to make sure that you're successful. That's what it's all about. All right, folks, till next time, stay safe. God bless, and hopefully you got something out of this long episode. And you know what? I usually don't do free episodes on the internet. So hopefully you got something out of it. Until next time, stay safe. God bless.